Bismillahirrahmanirrahim. Assalamu alaikum. This is Javeria Zafar. So today I will discuss the very main equation of quantum mechanics, which is the Schrodinger wave equation. Basically, you can say the quantum mechanics is based on this Schrodinger wave equation, which is given by the Erwin Schrodinger. He's an Austrian physicist. What is basically the Schrodinger wave equation is? The Schrodinger wave equation basically tells us the wave and the particle nature of an electron. So to discuss that Schrodinger wave equation, how it is derived, he proposed that if the electron has the wave nature, then it will obey all the same equation of motion as all the other known type of waves obey. If it means that the electron, if it obey the wave nature, so that wave nature will be the same, and they follow and obey the same equation of motion as all the other known type of waves obey. So he derive the equation and describe the wave motion of an electron along any of the three axes. So that is the x, y, or and z axis. He called this equation, which he has proposed, is called he called it a Schrodinger wave equation. To discuss this equation, so we consider the particle. You can see this is a particle P. It move in a circular path. See, you can see the arrow. It can move in a circular path with the velocity omega, and the omega unit should be in radian per second. So from point O, the particle, you can say the electron move from point O to P, so with the angle theta. This theta will be equal to omega t. This t is the time taken to time taken by the particle to travel from point O to point P. So consider this whole picture. You can see that the particle move from point O to point P. So this movement of the particle is typically like the simple harmonic wave equation. Simple harmonic wave. So this movement is shown here in the form of wave. You can see that this is the crust and this is the trough of the wave. So time taken from this point to this point is t. Here's the time, and this is typically the wavelength. So point O to this point is the crust. It is of lambda over omega, and from this point to this point is 2 pi over omega. So this is typically the you can say that the particle change its displacement. Displacement is the shortest distance. Displacement, the particle changes its displacement with respect to time. This is shown with the help of the wave. You can see that this wave, the amplitude of this wave is equal to the phi. This is phi, and this phi is typically the amplitude of the wave. It is a wave function. This is also called as wave function. So to derive the Schrodinger wave equation, we will consider this triangle. This point is typically extended downward from where the particle starts, and you can see this is a triangle. This triangle I have drawn here. So this triangle is typically I have drawn here. So the triangle PBC having the theta, and this is a right angle triangle. You can see the perpendicular of this right angle triangle is equal to phi, and psi, and the hypotenuse of this triangle is equal to the A. It is this A is the radius, you can say the radius of the circle, and the circle is a path of the particle in which the particle changes its displacement with respect to time. So to consider this theta, if we take the sine of this theta, the sine theta will be equal to, we know that we have studied the trigonometric rules. So sine theta will be equal to perpendicular over hypotenuse, and this perpendicular you can see from the triangle, it is equal to psi, and hypotenuse will be equal to a. So the a, make sure that the a is the radius of the circle, and psi is the vertical displacement of the harmonic wave, you can say the amplitude. So if we rearrange this equation in this form, that is only the a move to the sine theta side. So this psi, that is the wave function, will be equal to a sine theta. Here theta, make sure here theta is equal to omega into t. The omega t will be equal to what is the omega? Omega is basically the angular velocity in radian per second, and t is the time. And if we replace this theta with the omega t, the above equation will become this omega is angular velocity, and it is equal to the, in this equation the omega will be equal to 2 pi nu. Nu is the frequency of this wave. So this nu is the frequency of the wave. How it come? How can you prove that this omega value is equal to this? We know that the time taken for the change in the displacement of the particle from from O to P will be equal to the theta over omega, and this theta will be equal to 2 pi. If we replace this theta with 2 pi, so this equation will become like this: 2 pi over omega. If we inverse this equation, we know that time is the inverse of the frequency nu. So t is equal to 1 over nu, or nu will be equal to 1 over t. If we put this t value, this value 1 over nu in this equation, we will get this 1 over nu is equal to 2 pi over omega. To substitute to evaluate the value of omega, we will transfer this new value to here in the right hand side. So the omega will be equal to 2 pi nu. This 2 pi nu is proved that this omega is equal to the 2 pi nu. So in this equation, the omega is replaced with this value which we have proved. So psi is equal to a sine omega t will be equal to, in this omega we will put 2 pi nu into t. Now the frequency concept is introduced in this equation. So to understand the nature of the wave, meaning how the wave travels, to study the nature of the wave, it is basically the progressive wave. How it travel, it is basically the amplitude psi we have drawn here. This wave travels in a progressive way like this, with the wavelength this lambda. So this change in the wavelength will be equal to x centimeter. So this is a progressive wave. Progressive wave, one complete wavelength will be the lambda. Here the crest and the trough will be equal to lambda. So to understand the nature of the wave, we may consider the fundamental distance time relation. So to wave nature of the wave can be understand when we consider the fundamental distance time relation. So distance time relation, we have studied that the distance will be equal to the velocity of the body with respect to time. Any time taken to multiply the velocity of that body with the time, we will get the distance. So if from this equation, if we evaluate the t value, the t will be equal to x over v. So in this equation, the t value will be replaced with x over v. So this psi will be equal to a sine 2 pi nu x over v. Afterwards, we know that this new we have considered the frequency. It is equal to the velocity of the wave it travels and the wavelength of the wave. So if we replace the new value, this is the equation which we have which we have derived previously, in which the frequency concept was introduced, and this frequency is taken outside. So to evaluate the value of this frequency, so this a sine 2 pi x over v, we will introduce the value of frequency. The frequency will be v over lambda. This v is cancelled, so the psi is equal to a sine 2 pi x over lambda. To know that the two variables, which is x value, which is a displacement, or you can say the wavelength, it changes, then the value of psi is also changes. So if we differentiate this equation with respect to x, so this equation, to see that how the x changes, then the psi value changes. So to differentiate it, we take the d psi, we differentiate this equation. So the rule of the differentiation is that when we differentiate such equation in which the theta is present, the theta is also differentiated separately. You can see that this d over dx is differential of this, and this d of dx is the differential of this theta which we have taken. We have seen that this value a, and in the angle 2 pi over lambda, is a constant value, only the x changes. So if we differentiate this sine theta value, sine this value, the sign will be changed to cos, and this theta value here, the d over dx over dx will be equal to 1, and 2 pi over lambda are constant, so the value of this term will be 1. So this equation will become like this. We take this 2 pi over lambda, which is a differential of the theta. So we've taken first this product will be equal to this. So a cos 2 pi x over lambda here, and 2 pi over lambda here separately. So if we differentiate again this equation with respect to x, the you can say that we have taken the double differential. Again this equation is differentiated, double differential is taken, so the same we get the answer. Again the theta value is separately differentiated, so the value we take, we here make sure that the when we take the differential of a cos, this theta, this cos will be changed into sine, theta will remain the same, and the sine will have the negative sign value. So this theta differential value is multiplied with this, and this whole value, after taking the double differential of this equation, we get this value. If we compare this value, this equation with this equation, we can say that this whole value can be replaced with this psi value. See, so d square psi over dx square is equal to minus 4 pi square over lambda square, and this value is replaced with psi. Here you can derive like this. So this equation is when rearrange only to bring this this value equal to this value towards the left hand side. This minus value will be changed to plus value. So this equation will be like this. Now to show that the electrons show the particle nature, we will replace the lambda to the momentum value. Previously we have discussed that the wave nature of the electron. So now we will discuss the particle nature of the electron. You can say any particle. So it is not typically, this equation is not typically for electron, so you can say other particle also. So the electron and particle nature can be studied. So we use de Broglie's equation. The de Broglie's equation will be equal to lambda, that is the wavelength of the wave, is equal to h over mv. This h is a Planck's constant and mv is the momentum of the electron. So if we consider this lambda value, we have to put this lambda value in this equation. Here the lambda is in square, so we will this equation we will square of this the equation. Lambda square is equal to h square over m square v square. We will inverse it because the lambda is in the form of 1 over lambda square here in this equation. So this equation is inverse, and this 1 over lambda value is separately written in this equation. You can see this 1 over lambda value I have written in a separate multiple. So this value here, the 1 over lambda square is replaced with this. You can see this. So multiply this value, the psi value, after rearrangement this equation we get this d square psi over dx square plus 4 pi square m square v square over h square. Psi is written separately. This is all equal to 0. Now to make the concept of the energy in the above equation, we will use the Bohr's concept. The energy concept can be explained with this equation. In another way, you can say that you will introduce the concept of energy. We will make use of the Bohr concept, which is that the total energy of the system will be equal to kinetic energy, the sum of kinetic energy and the potential energy. The kinetic energy we have seen for any body, the kinetic energy will be equal to 1 by 2 m v square. So the potential energy we have replace it with the v, and total energy is represented by E. Rearrange this equation to have the v square value, v square value, v square velocity concept. This equation is rearranged, so we have uh, rearrange this equation to have the value of v square. So this v square value will be equal to, from this equation 2 over m is into E minus v. Now previously we have discussed this equation. We have derived this equation. Here the velocity concept is replaced with the energy value. So energy concept, see this velocity value which is evaluated previously, which is equal to 2 over m E minus v. Here velocity value will be replaced with this value. I have written this v value separately, and this psi value with this value is written here. V square value is replaced with this value. See, this m square is cut with this m, so this 2 is multiplied with this. 2 multiplied by 4 is 8 pi square, m is single, this E minus v, and this psi is separately written, and over h square, this all will be equal to 0. This equation is called the Schrodinger wave equation for the particle moving along the x-axis. Along all the other 3 axes, the equation above equation, this equation will be changed like this. Here the concept of 3 axes will be introduced. We will take the partial values. So curly square psi over curly x square along the x-axis, plus curly square psi over curly y square along y square, plus curly square psi over curly z square along z square. Here the value is the same. This will be equal to 0. And in this equation, this equation can be more simplified using the Laplacian operator. Now, what is a Laplacian operator? So the operator to tell us the divergence of the gradient of the function. Gradient mean the change, how the function change, what will be its divergence, how it change, within what respect it change. This is represented by Laplacian operator. In this equation, this whole value, this factor, this is the change of psi along the x, y, or z, and this is not the change. Psi will be the same, so the axes are changed. So the divergence of the gradient of the function is represented by Laplacian operator. So Laplacian operator is given with the is represented by del square. This is called the del squared. So in this equation, except the psi, this value, psi value, all of this will be equal to del square psi. Psi is separately written. You can say that in this equation, Schrodinger wave equation, along all the axes, the curly square and curly x square plus curly square over curly y square plus curly square over curly z square will be equal to del square. So this equation which we have discussed is now replaced with Laplacian operator. Laplacian operator will be replaced. So this equation will become del square psi plus 8 pi square m over h square e minus v, psi is equal to 0. So this is a more simplified form of the Schrodinger wave equation. Other forms can also be written. Other forms of the Schrodinger wave equation can also be written. If we take if we take this equation, this is the simplified form with the Laplacian operator. We take this equation. What we have done is that we have multiplied this value with this and psi value with this. Similarly, with the v value, we multiply this and this value. We get this equation. So if we multiply both sides of this equation with the h square over 8 pi square m, so that this whole factor will be cancelled. So if we multiply the above equation with this factor on right hand side and on the left hand side, we will have finally this equation. In this equation, the value of psi here is, you can say, is confined. So here the e value, we have rearranged this equation. E psi is equal to this value when we have moved this value from equal from here this side to this side. This whole value have the negative side. So the e psi will be equal to this. Here the psi value is common, and this whole value, after taking the common psi value, this value will be equal to h. H is another operator which is called Hamiltonian operator. And this operator, why we take the Hamiltonian operator? Hamiltonian operator basically tell us it is equal to the, basically it tell us the sum of the kinetic energies and the potential energy. So Hamiltonian operator is used. So this is all about the Schrodinger wave equation. Thank you so much for watching. Please subscribe my channel. Thank you.